Yeah, you can spell most things, right? Not all, most. Now, I think you could probably guess at this point, like, a big part of your quiz 2 classes from now, right? So these decay equations are, one of the things that you definitely will be expected to do, perfect. And they're not that complicated. You just absolutely need to know for, the next year plus that an alpha particle is 2, 4, the beta is -1 and 0, and the gamma is 0, 0. You have to know those things. All right, so I want to talk next about some of the properties of these 3 decay products. First, I'd like to talk about the ability of these 3 things to penetrate into materials, and then we'll talk about their ability to ionize materials. All right, so alpha particles cannot penetrate very easily through things. All right, so alpha particles have the poorest penetrating ability, and the main reason for that is their charge. Right? They have a 2+ relative charge. Right? So that means that they like to interact with things, they like to be attracted to electrons, they like to be repelled by nuclei. So they don't penetrate very well, primarily due to those electrostatic repulsions and attractions. It also doesn't help that they are bigger in size and mass than the other decay products. But the charge is actually the main reason they don't penetrate very far. So what's very far? A piece of paper would be pretty effective at blocking an alpha particle. All right, so alpha particles aren't that great at burrowing into things. Beta particles can penetrate more easily than alpha, and the main reason for that is that they only have half the charge of the alpha particle. And so there's less of an electrostatic repulsion or attraction with nuclei and with other electrons. And again, they are a little bit smaller both in volume. They're a lot smaller in volume. They're quite a bit smaller in mass, so that also allows them to penetrate a little better. But again, charge is the big thing here. So a beta particle can pretty effectively be blocked by like a piece of aluminum foil. Gamma radiation can penetrate much better than these particles. All right. Gamma has no charge. It has no mass. It has no volume. Right. So it can penetrate way easier. And lead came up before, right? Jordan brought lead up. We typically use lead vests not to block gamma photons, but to block who? X-ray photons. But X-ray photons and gamma photons, it's the same thing, just gamma is a little bit higher frequency, right? Gamma is a little bit higher energy, but they're the same thing. They're right next to each other on the electromagnetic spectrum. So yeah, it shouldn't be that big of a surprise that we use the same thing, that we can block gamma with some lead. Now, I'll pass these around. I do have some radiation detectors. These are actually not Geiger counters. I believe it's a different style of device. And the way that these things work is that, let me shut up for a second. You hear that? Hear that? You actually, yeah, so there's little clicks. Each time there's a click, that means that the important part of the detector detected something, an alpha, a beta, or a gamma. Maybe these would respond to X-rays too, I'm not sure. And it's really nothing to worry about. There's background radiation all over the place, and it's not a big deal. So I'll pass these around. The way that these work is you just have to hold in this button. All that the red light means is that you are successfully holding the button in. And then you can listen for the click. The needle also might kick over, but yeah, we can pass these around. All right, so the other property, and then I do want to talk a little bit more about the scintillation counters, is the ability of these 3 things to ionize material. So when we talk about ionizing, we mean causing a neutral thing to become a charged thing. Like an ion is just a charged atom, right? And the way that we ionize something is to rip an electron off of it. We can't mess with the nuclei very easily. We're going to get into some quantification of that in topic 6 or 7.3. So if we ionize something, it's because we're knocking an electron off. All right. So some forms of radiation are known as ionizing radiation, and we would classify radiation as that if it's able to pretty effectively knock electrons off of things. So examples of types of radiation that are ionizing, well, are actually all three of these. And then X-rays have the ability to knock electrons off pretty effectively also. So those four things, and I'm not really aware of any other, we sometimes call ionizing forms of radiation. And then non-ionizing radiation would be radiation that isn't very effective at knocking electrons off. So visible light. It can knock electrons off, and in some things like what we call them solar photovoltaic cells and my MOVA globe, right? Visible photons do knock some electrons off things, but it's very uncommon for visible light to be able to do that. Microwaves aren't particularly ionizing. Radio waves, infrared, right? Ultraviolet. Those are commonly called non-ionizing. So even though we said that all three of these are ionizing forms of radiation, they're not equal at their ionizing ability. So alpha and beta are able to better ionize things because of their charge. All right. So because an alpha particle has a charge, 2+, it can influence electrons pretty easily. A beta particle and an electron has a negative charge, so it can influence electrons pretty easily also. Gamma radiation, yep, it can knock electrons off things, but because it's not charged, it's not as effective as our charged particles. Yeah, Brian?
So like alpha particles would like take electrons and beta would just like knock them away?
That's a healthy way to think about it, yes. And probably most of the time that would be pretty accurate. Yeah, Jordan?
If you lose distance like Chernobyl where there's
Okay.
still radiation,
Yep.
would you be bombarded with alpha and beta particles as well?
Alright, so if you went to Chernobyl, yes, this thing would definitely click more frequently than it does here. But let's take a second and address who is making these things click. Alright, so I think we'll get to this today. We're actually going to go to an EPA website that allows us to calculate our annual ionizing radiation dose. So we'll actually get a very good look at the environmental factors that can emit some radiation. But in this room, probably most of the radioactive materials would be in the cement of the concrete blocks. Cement is mild, has some mildly radioactive constituents. We mentioned radon earlier. So depending on our underlying geology, like some minerals have a little, there's a few. Let me get this right. I think it's lead, maybe uranium. Lead and uranium can decay into radon, and then there's a whole decay series. But the fear about radon is it accumulates in your basements from the underlying geology. Radon, what's the atomic mass? It should be in your periodic table somewhere. It's a noble gas.
86.
86. So it has 86 protons. You think that's more dense than nitrogen and oxygen, or less dense than nitrogen and oxygen? More dense. So guess what it does if it's in the room? Like it sticks to the floor. Right? That's why we test for it in our basements, because it's like heavier than air. It's mostly accumulates in our basements. So I forgot where I was going for a second. So most of the radioactive things that might be emitting radiation in this room would be in the walls and then coming up from the floor. So when I hold this in here, what is it detecting? Is it detecting alpha particles? Probably not. Why not? Because what, Miles?
They stop so easily.
Yeah, an alpha particle gets stopped so easily. All we need is a piece of paper. So there's not paper in between the walls and me, but there's air. And I don't know, 10 feet of air has got to be at least as thick as a piece of paper, at least as many molecules as a piece of paper. So I don't think there's any alpha hitting this, or at least not much. What about beta? Same deal. Not really. Doesn't take a whole lot to block beta. So unless there's beta being generated right here, maybe there's a carbon dioxide molecule that happens to be carbon-14, sure. That could do a beta decay, it could happen right next to it. but it's gonna be almost entirely gamma that this thing is detecting. And even if we went to Chernobyl, that would still be the case, right? Because the alpha and beta get blocked really easily. Yeah, oh, you can just hold on to it. Yeah, Patrick.
So none of their like watches that like the inside has like I guess radioactive elements or something. So like,
Yeah, that's gonna show up on our EPA thing, yeah.
so is that gamma radiation?
I don't know. I don't know. Liam. Oh my, why is it was really you in bathroom? Alright, now I have a question up here that we haven't addressed yet. Well, maybe we sort of did address it. Let's see if you can figure it out. So even though, alright, we care about ionizing because as like an organic like being, right? Like I don't want electrons to be knocked off of my molecules. That's not good. That makes them super chemically reactive. I don't want to be chemically reactive, right? So alpha and beta, I want to definitely keep those away from me. Gamma, not going to knock electrons off as easily, but usually we do care way more about gamma. So can you talk in your foursomes and see who's already clued into why that is, right? And then we'll compare momentarily. It sounds like we're almost ready. Let me just put my scintillation counters away and then we'll compare. Okay. Let's see, Patrick, what we came up with. Sarah, what came up in your group?
Excuse this interruption. Would the following students come down to the media center now to pick up their sticky bun order? Would be Brian May, Grace Wang, Sarah Bernardi, Stephanie Smezik, Melissa Dong, Burton Yee, Allison Paglia-Bond, Kristen Langle, Brian D. Agostino, Jacob Thorpe, Liam Weldon, Tom Leon, and Sean Hammond. Have a great weekend.
All right, Sarah, you are not among the announced. So why gamma? Isaac, relax.
Wait, Jake, stop.
Yeah. So Sarah said that the sticky bombs are seriously causing this big of an uproar. Sarah said that the gamma rays aren't as easily blocked. Absolutely right. I mean, if Kevin's shooting alpha particles at me from right there, right? Even if they make it through the air to me, I've got skin. I've got like tissue. Like my organs are protected. I'm not that concerned about it. If Isaac shoots beta particles at me, same thing. Like maybe they get to me, but my skin's probably almost as thick as aluminum foil. If I include my tissue underneath, then that's good. So those things aren't going to really get inside me. But if Brian all the way back there shoots gamma at me, it's going to reach me, and I'm not an appreciable thickness of lead. I'm not going to block that stuff very well. So it can get inside me pretty easily. So gamma is often the larger concern. Now, when would alpha and beta be a concern? Like, what's the biology word you use? Like, I'll probably use it wrong. What are the vectors where the alpha and beta can get inside me? Apparently I used it wrong. Or what?
Oxygen?
You can breathe it. All right? You can breathe it in. It can get into your lungs, and I might care about my lung molecules getting ionized. Sure. Brian?
If you eat or drink anything that...
Yeah, you could ingest it. You could eat it or drink it. Sure. I can think of a couple of other ways. Yes, it could be injected into you. It wasn't that long ago, maybe 5-6 years ago. Like I want to say it was like a former KGB operative, was assassinated with being injected by nuclear material. It was in it was in the 2000s, not even the 1990s. So you could inject it, stab, right? But if it gets inside you, that's when it's going to be a major problem. Otherwise, gamma is the one we care about most. All right, now this I think I stole directly from your textbook. This very succinctly compares our three different types of decay particles. I'm just in the interest of time, I'm going to point out the few things here that we haven't said already. So one of those things is there's a row for speed, all right? So gamma rays travel at the speed of light, right? So it's super fast. Beta particles can travel quite fast, up to 90% of the speed of light. Alpha particles, because of their relatively large mass, we're talking up to 10% of the speed of light. Penetrating effect, that's what we've just talked about, but there's some additional information here. So alpha particle can be blocked by a thick sheet of paper, this says, by skin, or by a few centimeters of air, all right? Beta particle, a few millimeters of aluminum or some other metal. And then gamma is slightly inconsistent with what I said. Never completely stopped, but we can reduce the intensity. All right, so we can take some of the energy out of individual photons, we can redirect photons, but never completely stopped. The other thing, which is a great link to topic 6, would be, can we mess with these things using some of our fields that we've talked about? So an alpha particle is charged. Can we affect the alpha particle with an electric field? Yes, because a charge is going to be felt by an electric field. Can we affect it with a magnetic field? Yes, a moving charge acts like a magnet, and magnets are affected by other magnets. So we can and will influence the motion of an alpha particle with electric or magnetic fields. Same deal with the beta particle, because the beta particle is charged, right? But the direction of the electric force or magnetic force on the beta particle would be opposite the direction of the alpha particle. We'll see that more in topic 9. Gamma ray not being affected by fields whatsoever. All right, I do want to get to that annual dose of radiation before we leave, so I'm going to buzz right through my introduction to biological effects of these things. We don't completely understand the mechanisms. We don't completely understand what these things do when they enter, organic material. But we do know that if they knock electrons off, there's going to be some chemistry that takes place. There's going to be some rearrangement, not just of electrons, but of molecules. And what we care about is if there's going to be reorganization in our DNA. That's what we're particularly concerned about, and we'll talk a little bit more next time. All right? And then the other thing I'll say, and then we better get to this calculation, is the EPA does issue concentrations that are safe for chemicals. Like there can be up to 2 parts per billion lead in water. There can be up to 20 parts per million, whatever, benzene. For radiation, there is no safe amount, right? So any individual ionizing particle can do damage that matters. All right, so anyway, let's get to this. The way that I'd like to do this is whoever in here, whoever in here has the worst result is what we will use. All right? So some of these things we can't even control. So the first thing here, and I'll make this a little bit bigger, cosmic radiation at sea level. So ionizing radiation comes in from outside of the Earth. There's nothing we can do about that. We could live underground, but we don't want to do that, right? So 26 millirems, the rem is the unit we're talking about here. 26 millirems, right, we can't do anything about. All right, what is the elevation of your TAM? So if we are higher, right, then there's less atmosphere that the cosmic radiation is going through, so we get more, all right? So we're lucky that we are very close to sea level. We're probably, 70, 80 feet above sea level here, so we're definitely up to 1,000, the lowest one. We're probably closer to 0 additional millirems, but whatever, we can't do that. What region of the U.S. do you live in? So we said the underlying geology plays a role. We are Atlantic coast, which is good because we don't have granite underneath us, which would be what the Colorado Plateau has and to some extent elsewhere. So we got the lowest amount there. We take in radiation from our food and water. There's nothing we can do about that. We take in radiation from the air, primarily radon. Short of not breathing, there's nothing we can do about that. Do you wear a plutonium-powered pacemaker? I'm guessing none of us do. So we saved ourselves 100 millirems. Do you have porcelain crowns or false teeth? Does anybody have that? Okay, good. We saved ourselves 0.07 millirems. Add 1 for each 1,000 miles traveled by jet this year. The easiest way to think about this is a time zone is about 1,000 miles wide at like our latitude. I think I'm at 14,000 miles for the past year. Like one trip to Hawaii and one trip to Ohio. No, not Ohio, one trip to Chicago. Can anybody beat that? 14,000? Anybody go to like Asia? Yeah.
I went to Hawaii and St. Louis.
Hawaii and where?
St. Louis.
St.
Missouri.
Louis. Yeah, that's about the same as me. Jordan? London once?
We've never done.
I think London's about closer to Hawaii, I think.
Yeah.
Alright, so Lauren and I are the same, so I'm going to call that 14, because we added 1 for each 1,000 miles. X-ray luggage inspection, yeah, everybody does that. Anybody camp with gas lantern mantles?
Yes.
Alright, so that's a yes. I'm afraid that we've run out of time. So, yeah, we'll probably redo this next class. Alright, so you don't actually have like official homework, but medical isotope presentations in just over a week. So get cracking on those.
So,